Hello everyone. So the next topic which we are going to start today is hydraulic machines. Now what actually are these hydraulic machines? These hydraulic machines are actually the part of fluid machines. Okay, when we classify these fluid machines on the basis of the type of working fluid used. So the type of working fluid used can be either liquid or it can be gases. Okay. So when the liquid is used as a working fluid, then the machines are termed as hydraulic machines, because when I say liquid, in most of the cases, in almost every cases, water is used as that liquid. Okay, so when the liquid is used as the working substance, then those machines are called as hydraulic machines. It can be either hydraulic turbine or it can be hydraulic pump. Okay, and when gases are used as the working fluid, then it can be either gas turbine or it can be gas compressors, okay, or it can be fans or blowers and so on. Okay. So when we study this portion, that means when the liquid is used as a working fluid, when we study this portion, then this comes under hydraulic machines, under the subject name of hydraulic machine. And when we study this portion, this comes under the subject name of turbo machinery, which you have if you have studied that subject in your engineering, turbo machineries. There we study about the gas turbine and compressors. Okay, so what we have to do now is we will confine our study to this hydraulic machines only. That means we will be studying about the machines, about turbines, about pumps using liquid as the working fluid. Okay, now what actually is this hydraulic machines? So how can we define machines? Machines are the devices which can convert one form of energy to some useful form of other energy. Okay, which convert one form of energy to useful form of some energy. Okay, and what are the hydraulic machines? Hydraulic machines are the devices which can either convert hydraulic energy to mechanical energy, which can either convert hydraulic energy to mechanical energy, or it can convert mechanical energy to hydraulic energy. Okay, so if we are having the machine, if we are having the energy in the if we are having the hydraulic energy, and with the help of machine we are converting it to mechanical energy, then such devices are termed as turbine. So what we do in turbine is we have the energy in the form of hydraulic energy, in the form of water power, and then we convert it into mechanical energy, and further that mechanical energy is converted into electricity. That we are not going to deal, we will just deal up to the conversion up to mechanical energy. Okay, so such devices are known as turbine, and when mechanical energy is converted to hydraulic energy, then such devices are termed as pump. Okay, so what we do in pump, we have the mechanical energy, of course, in the form that mechanical energy is from electricity only, but finally we have the mechanical energy, and with the help of that mechanical energy we convert it into the hydraulic energy, we convert it into pressure head, and finally so such machines are termed as pump. Okay, so hydraulic machines, how can you define hydraulic machines? The machines which can either convert hydraulic energy to mechanical energy, for example turbine, or which can convert mechanical energy to hydraulic energy, for example pump. Getting this? So okay, so this is how we can define this hydraulic machines. Now first coming to the turbines. Now, so what actually are the turbines? As I told you, turbines convert hydraulic energy to mechanical energy. Okay, and when I say hydraulic energy, I basically mean two types of energy. First is the kinetic energy, and second is the pressure energy. Okay, so basically these two types of energy are only converted to mechanical energy. There are two more types of energy, like intermolecular energy in fluid, or potential energy, but these can not be directly converted into work. Intermolecular energy generally we do not use, we cannot use in fact, because if you remember the thermodynamics part, we have discussed about the intermolecular energy, and there I told you that suppose if we are heating the fluid, we are providing the intermolecular energy of the fluid will increase, and that will convert into work, but that conversion will not be 100% conversion. So this intermolecular energy is actually the low grade of energy. So 100% conversion of that energy is not possible. Okay, so if, obviously it will not be efficient to use such energy, and obviously potential energy cannot be directly used. It has to be converted further into kinetic energy or pressure energy to use it further. So when I say hydraulic energy, I mean two types of energy. It can be either kinetic energy or it can be either the pressure energy. Okay, now we will see the classification of turbines. How can we classify the turbines? Okay, so the very first classification is on the basis of energy at inlet. On the basis of energy at inlet. Okay, what type of energy is available at inlet? So in this classification, the very first is the impulse turbine. Okay, what are impulse turbine? The turbines which have just kinetic energy at inlet, that is not having the pressure energy. As I told you, two types of energy can be converted. First is kinetic energy, second is pressure energy. So the turbines which just have kinetic energy at inlet and not the pressure energy, such turbines are known as impulse turbine. Okay, the turbines which have only kinetic energy at inlet are termed as impulse turbine. Okay, for example, Pelton wheel, Gourard, then you have Banki turbine, Jonwald turbine, and turbo impulse wheel. Okay, so all these turbine has only kinetic energy as input, so such turbine are termed as impulse turbine. Okay, second classification, second type of turbine is the reaction turbine. Okay, reaction turbine means the turbines which have kinetic energy as well as pressure energy both at input are termed as reaction turbine. Okay, the turbines which are having both kinetic energy and pressure energy at inlet are termed as reaction turbine. For example, the Francis turbine, then you have Kaplan turbine, propeller turbine, Thomson turbine, Fournier-Yon turbine, etc. Okay, so all these turbines are reaction turbine which has both kinetic energy, here both kinetic energy and pressure energy at input, and here only kinetic energy at input. Getting this? Okay, so this is the first classification on the basis of energy at inlet. Now next classification is on the basis of type of flow within the turbine. Okay, so second type of classification is on the basis of type of flow within turbine. For example, the very first is the tangential flow turbine. Okay, now what is tangential flow turbine? Tangential flow turbine means the center line of the jet will hit tangential to the wheel of the turbine. Then such turbine are known as tangential flow turbine. Okay, for example, the Pelton wheel turbine, then turbo impulse turbine, etc. Okay, when the jet is hitting at the tangential of this wheel, then it is termed as the tangential turbine. I will show you with the help of one diagram like this. This is the Pelton wheel turbine. We will get into the details of Pelton wheel turbine. Okay, so how is the jet hitting in this wheel? The jet is hitting in the tangential direction, and this turbine will rotate. Okay, so such turbine are termed as are called as the tangential flow turbine. Okay, then you have the second type of turbines are the axial flow turbine. Okay, so what are the axial flow turbine? In which the water is entering and leaving from the turbine in the axial direction. Okay, so I will for example the Kaplan turbine, the propeller turbine, Johnwell turbine. Okay, that means the fluid is entering the turbine and leaving the turbine in the direction parallel to the axis of the turbine. Okay, like this. This is the figure of Kaplan turbine. Okay, so how is the fluid entering here? You can see this is the turbine. The fluid is entering in the direction parallel to the axis of turbine, and this is leaving also in the direction parallel to the axis of turbine. Such turbines are called as the axial flow turbine. Okay, now third type of turbine are the radial flow turbine. Okay, so when the fluid is passing through the runner in the direction perpendicular to the axis of turbine, when the fluid is passing through the runner in the direction perpendicular to the axis of turbine, then it is termed as the radial flow turbine. Okay, for example, the Francis turbine, Thomson turbine, Goddard turbine. Okay, now this radial flow turbine can be either inward radial flow turbine or it can be either outward radial flow turbine. Inward radial flow turbine means when the water is entering from outside to inside in the radial direction. Okay, then that is called as the inward radial flow turbine. So these are the examples of inward radial flow turbine only. The Francis turbine, Thomson turbine and Goddard turbine, these are the inward radial flow turbine. Okay, I will show you the Francis turbine. Okay, so this is the Francis turbine, you can see here. Okay, the water will enter and exit from this turbine in the radial direction. Okay, so these are the guide vanes. We will get into the details of all the turbine, don't worry. Okay, these blades are guiding the water and finally it will enter into this turbine in the radial direction, and it will also leave this turbine in radial direction only, from radial direction only. Okay, so such turbines are called as the radial flow turbine. Inward radial flow turbine means water is entering from outside and coming inside. Outward radial flow turbine means water is coming from inside and getting outside. Okay, so I told you the example of inward radial flow turbine, Francis turbine, Thomson turbine and Goddard turbine. Okay, similarly outward radial flow turbine, the examples are Fourneron turbine. Okay, so this Fourneron turbine is outward radial flow turbine. Getting this? Okay, now next is the mixed flow turbine. Okay, mixed flow turbine means it changes the direction from radial to axial or axial to radial. That means it enters in the radial direction and exits in the axial direction. Such turbine are called as a mixed flow turbine. Okay, for example, modern Francis turbine. This modern Francis turbine is a mixed flow turbine. Okay, next classification is on the basis of available head. How much head is available? On the basis of that available head, we can classify the turbine. Okay, so that turbine can be either a high head turbine. High head turbine means the head is above 250 meter. Okay, for example, Pelton wheel turbine. Pelton wheel turbine is a very high head turbine. There we need water at a very high head, then finally that is converted to the kinetic energy. Okay, next type of turbine is a medium head turbine. Okay, where the head lies between 60 meter to 250 meter. For example, Francis turbine. And third type of turbine is a low head turbine. Okay, if the head is below 60 meter, then that is termed as low head turbine. For example, Kaplan turbine and propeller turbine. Okay, so that Pelton wheel turbine is a high head turbine having head greater than 250 meter. Francis turbine is a medium head turbine having head between 60 to 250 meter, and Kaplan or propeller turbine is a low head turbine having head below 60 meter. Okay. Now, next classification is on the basis of specific speed. Okay, now what actually is the specific speed? We can define the specific speed ns is equal to n root p upon h raised power 5 by 4. Okay. Now what does this mean? What is the specific speed? The specific speed is the speed of the geometrically similar turbine if it develops unit power under unit head. Okay, that means if we are having the geometrically similar turbine, okay, geometrically similar turbine of the original turbine, if we are having such that turbine develops unit power 1 kilowatt power under unit head 1 meter head, then that is termed as the then the speed of that turbine is termed as the specific speed. Okay, speed of the geometrically similar turbine. Geometrically similar means the turbine which is identical in shape, which is identical in blade angles. Such turbines are geometrically similar turbine. So the speed of this geometrically similar turbine which would develop unit power when working under unit head is called as the specific speed. So on the basis of this specific speed also we can classify the turbine. So very first is type of turbine is the Pelton wheel. So the specific speed of this Pelton wheel lies between 10 to 35. Okay, second is the Francis. Specific speed lies between 60 to 300, and third is the Kaplan or propeller. The specific speed lies between 300 to 1000. Okay, now so this is specific speed ns. We will get into details of a specific speed as well. Ns is equal to n root p upon h raised power 5 by 4, where n is speed in rpm, h is net available head, and p is power in kilowatt. Getting this now? Okay, so this is how we can classify the turbines. Okay, so very first type of turbine which we are going to study is in fact most commonly used turbine, which is Pelton wheel turbine. Okay, so if I classify the Pelton wheel turbine, I have already told you the classification. So this Pelton wheel turbine is an impulse turbine. This is a tangential flow turbine. Impulse turbine means only kinetic energy we are having at input of the wheel. Okay, then this is a tangential flow turbine. The water is striking in tangential direction of the wheel. Okay, then this is a high head turbine. As I told you, the head is more than 250 meter. Then this is a low specific speed turbine. The specific speed is between 10 to 35. Okay, and then this is a low discharge turbine. Low discharge turbine means the discharge is very low. In fact, the jet used there is of very small size, so the discharge there is very less. Okay, so this is how we can classify this. It is an impulse turbine, tangential flow turbine, high head, low specific speed, low discharge hydraulic turbines. Okay, now I will tell you the how this Pelton wheel functions. So this is how the Pelton wheel works. So we are having the water at a very high head, as I told you. So this is the dam in which we are having the water in reservoir, and with the help of this penstock, this water is then transferred to the jet, and from this jet, here we were having the water. The energy was in the form of potential energy. That energy is converted to kinetic energy with the help of this jet, and with that high kinetic energy, that jet strikes this wheel, the Pelton wheel. The jet strikes this Pelton wheel, and with this Pelton wheel will rotate, and finally connected to this wheel will be a shaft which finally rotates in the generator to generate the electricity. Okay, so this is how this works. Now the very first terminology you can see here, very first thing is this Hg. This is nothing but the gross head. Gross head means total head available. The water is available at a head of Hg. Okay, so this Hg is nothing but the gross head. Okay, now while transferring the water from this head race up to this point, there will be certain losses because of friction, etc. Okay, so that losses are nothing but hf are the friction losses. Okay, so the net head, what would be net head now? Gross head, as I told you, is the total available head. Total head which was available is nothing but the gross head, but the net head is obviously less than the gross head because there will be certain loss because of friction. And then we are having the tail race, the nozzle we are having at a distance of small h from the tail race. Okay, so this head is also will also be subtracted. So what is the net head available? So net head available h is nothing but total gross head hg, okay, minus this friction loss hf minus this tail race height h. Okay, so the total gross head available was hg, but the net head available is only hg minus hf minus h. Okay, so whatever power is available at the nozzle, that is because of that because of the net head available. Okay, so what will be the water power now? So water power at inlet of nozzle, so that is nothing but rho g qh. Total water power, as we know, is rho g qh, where this h is nothing but the net head of the net head at the nozzle inlet. Getting this now? Okay, now considering these 2 points, suppose this is point 0 and here we are having point 1 where water is coming out of the jet. Considering these 2 points, we can apply Bernoulli's equation between 0 and 1. So applying Bernoulli's equation, okay, so what does the Bernoulli's equation says? P naught by rho g plus V naught square by 2g plus Z naught is equal to P1 by rho g plus V1 square by 2g plus Z1. Okay, now very important thing here, at this point the pressure is equal to atmospheric pressure. Okay, that means 0 gauge pressure, so this can be taken as 0. At outer point, the nozzle is again diffusing the jet into the atmosphere. Again we are having the atmospheric pressure. Okay, now the velocity at this point is again 0, so this is also 0. Okay, so we are left with this much only. So here Z naught, what is Z naught? Total gross head is hg minus the loss, which is hf, okay, minus Z1. Okay, what is Z1? Minus small h, this is nothing but V1 square by 2g, and this hg minus hf minus h is nothing but net head h. Okay, or you can say h is equal to V1 square by 2g. Okay, or you can say this V1 is equal to under root of 2gh. Okay, so this is how you can calculate the velocity at inlet of turbine. If you are having the head, the net head if you are having, then you can directly calculate the velocity at inlet of turbine. Getting this or not? Okay, now suppose if Cv is the coefficient of velocity here, then this V1 will be equal to Cv under root of 2gh, where Cv is the coefficient of velocity. Getting this now? Okay, now coming to this blades. Okay, so this is how the blades of Pelton wheel turbines are. These are double semi ellipsoidal in shape, like this you can see here, and double blades are given in order to cancel the axial thrust. Okay, because if only single side blade is given, then there would have been the axial thrust. Okay, so if the jet is striking here, okay, it will deflect this in this direction, okay, as well as in this direction. So this is how the axial thrust is balanced. Okay, so this is why the double blades are used in this Pelton wheel turbine. Okay, now we will come to the velocity triangle. We will draw the velocity triangle now. So here these are our double ellipsoidal blades. Okay, and the water is striking at this point. As I told you, the water is striking at this particular point with a velocity, suppose u. Okay, with a velocity, suppose v1. Okay, so this water jet is striking with a velocity v1,